In this tutorial, we're going to show you how to first create the geometry related to the project of the truck aerodynamics. After creating the geometry of this project, we're going to import it into the ANSYS meshing software in order to create tetrahedral mesh cells over it. And after that, we will start the Fluent software and show you the needed settings in order to perform the aerodynamic simulation and investigation over the truck geometry. We will discuss y plus values, pressure distribution over the surface of the truck, the velocity of the airflow around it, and of course, calculating the drag lift forces that are exerted over the surface of the truck due to the passing of airflow over its surface. Alright, to start drawing the geometry for this project, what you have to do first is to actually click on a fluid flow block and then drag it over a blank space inside workbench environment and just leave the left key on your mouse. And then you have to actually first right click on the geometry and make sure that you click on Space Claim Geometry software. After that, you just have to wait for some time until the Space Claim software opens up. Okay, in the Space Claim software environment, what you have to do is to first import the geometry related to the truck. Now, it should be mentioned that the geometry, which is, will be imported actually into the software, has been taken from the GrabCAD website. So what I'm going to do next is that I will click on File, go over Open, and then I will look for the IGS format on the drop-down list here. And then you can see that this truck geometry IGS file will appear. Again, I should mention that this file has been actually taken from the GrabCAD website. Alright, this is the geometry that I was talking about. This is the truck along with its trailer, and if you actually expand the component, you can see different components which shows different parts of this geometry. Now what we have to do and what we need actually to do is to make all of these components, these 6 different components, into one component. So I will simply click on each of these components, and while holding down the control key on my keyboard, I will select the next solid part or component. Alright, now that all of the components are selected, I can simply right click on them and then select Move to New Component. As you can see here, all of the solid parts are now mentioned under the component 77, and you can easily delete all the previous components so by simply selecting them and then right clicking on them and then selecting Delete. I'm gonna have to delete this one as well. And alright, now what we have here is a united geometry in which different solid parts are available and are present. Okay, what we're gonna have to do is that I will actually pull the whole geometry up for like 1,000 millimeters in order to be able to draw a plane or a sketch so that the sketch would be tangent to the bottom of the wheels of the truck. So I'm gonna actually just select all the geometry in the Space Claim environment, and then I will have to simply go to the design and then select Move. And then you just have to go over and actually hover over the Z direction and just drag your geometry and you just leave it someplace, and you can simply then enter the value of 1,000 millimeter for the dimensions that you want to move your geometry. After that, you can easily see that the geometry would move to the extents and to the value that you have defined here for the pull command, for the move command, I'm sorry. Alright, after that I can simply deselect the move command, and in order to actually define a plane so that so to create a sketch over it, we can simply click on the Y coordinate system. Let's just make sure that I've clicked on it right. Okay, and then I'm gonna have to select this plane command. In this way, a plane would be created exactly in the middle of my geometry. Alright, after that I'm gonna have to actually draw a geometry, or actually I'm gonna have to draw an outline, which is going to be the the outer domain of our project. So after creating this plane, I'm gonna have to select the sketch mode command and just have to first look normal to this plane. Alright, now I'm gonna actually draw this outline, or my outer domain, as a rectangle or a cube. So I will have to select this rectangle command, and then I will go over and hover my mouse over the origin of the coordinate system. After that, you just have to hold down the shift key on your keyboard, and then you just can leave it. In this way, you can easily see that the software is showing you the location of the first vertex of the rectangle that you want to draw. So this rectangle that I'm going to draw would be placed exactly on the x coordinate system. So this is the first vertex of my rectangle, and the value that I want to shift it from the origin of the coordinate system would be equal to minus like 15,000 millimeters, which denotes 15 meters. Now the vertex of the rectangle has been placed here, and now you can easily see that the software is drawing this rectangle from this part, and it is now asking you for the dimensions of the height and length of this rectangle. Regarding the height of the rectangle, I'm gonna have to enter the value of 15,000 again, and regarding its length, actually I'm gonna enter a value of 50,000, which denotes to 50 meter. Also, it should be mentioned that in order to switch between the dimensions for both height and the length of the rectangle, you can simply use the tab key on your keyboard, so that it would shift between each of these dimensions. So as I actually hold the tab key on my keyboard, you can easily see that the dimensions would change from the length to the height of the rectangle. As you can see here, I'm actually hitting the tab key on my keyboard, and I can simply move between these two dimensions. Alright, these are the dimensions that we wanted to have for our outer domain. So I'm gonna have to click enter after that. I'm gonna rotate this geometry so that you can view it in 3D format, and then we can go and use the pull command, or actually we first have to click on end the sketch editing, and then I'm gonna use the pull command in order to turn this surface to a 3D object. But before doing that, we have to make sure that we actually hide this component, the whole different bodies of the truck. So all I have to do is to simply click on this tick, and then the whole component will become hidden. Alright, as was mentioned, I'm gonna have to select this pull command and simply click and drag this surface in the direction that I want. Now this is the one side of the outer domain, so I'm gonna actually do it again. Before leaving the left key mouse, you just have to define the dimension or length of the extrusion, for example. So I'm gonna actually enter the value of 15,000, and then as I click on the enter key on my keyboard, you can see that this extrusion process has happened for 15 meters. I'm gonna have to do the same thing for the other side, so I will have to select this surface and then drag it in this way, and before leaving the left key on my mouse, I'm gonna have to enter the value of 15,000 meter for this side as well. Alright, we have actually created our outer domain now, and we just have to change this. Alright, now if I just click here in order to show the geometry of the truck, you can see that this isn't the geometry isn't shown. So what I'm gonna have to do is that you can simply click on any surface or any point of this geometry. Let's just select the surface, and then simply click on this 3D object, 3D cubic object, and then use transparent. In this way you would be able to see the inner objects and geometries. Alright, Now we have both the outer domain and the truck geometry. The truck geometry has been counted inside our outer domain for 2 times. One time for the truck geometry itself and one time for the outer domain. So what we're going to have to do is that we're going to have to subtract the geometry of the truck from our domains. And we can actually do that by using the combine command. As a matter of fact, when you actually select the combine, you have to first select your outer domain or target body which you want another object to be subtracted from. So I will select this outer domain, and as for the, let's just select it again, and as for the the objects that we want to subtract from the domain, we're gonna have to first select this saw object, and then we can simply select this whole component 77. Now, as you saw, when I clicked on the component 77, the software created different solid parts for me while actually keeping the component 77. In order to prevent that from happening, you're gonna have to first, let me just do it again. And after clicking on the saw command, you just have to make sure that this keep cutter option has been disabled. Actually, when you enable this keep cutter, the software will make will not only perform the subtraction process, but will create a copy of this truck geometry inside your whole geometry as well. So I'm gonna have to actually disable this one in order to prevent the copying of different objects and bodies inside the geometry, and then I'm gonna have to select component 77. Now, as you saw, the different parts in the component 77 have been deleted, and there are some other parts available here which have been subtracted. Now, this is the only solid part that we want to have, which is the outer domain minus the geometry of the truck. So all I have to do is to make sure that select the each of these solid parts related to the geometry of the truck, and then I'm gonna have to right click on them and then select delete. Let's just delete the component 77 as well, and that's it. Let's just hide this plane too. And now what we have left is only the outer domain in which the geometry of the truck has been subtracted from. Now, if I actually perform this section mode, you can easily see that the entire geometry of the truck has been subtracted from our outer domain. So as you saw, I selected this section mode, and then I will actually have to hover over the Y coordinate system, and you can easily see that the geometry of the truck has been subtracted, and the inner geometry is empty. Okay, that's it for the geometry part. What we have to do next is that we're gonna have to close this Space Claim software in order to open up the ANSYS meshing. Okay, after closing the Space Claim software, we'll actually go back to the Workbench environment, and in the same block we're gonna have to double click on the mesh and wait for some time until the ANSYS meshing software opens up. Okay, after the ANSYS meshing opened up, you're gonna have to again wait for some time until the geometry becomes attached to the ANSYS meshing software. After that, the first step would be to define different names and actually create names for different surfaces and boundaries in your geometry. So in order to do that, actually, I'm gonna have to select this face selecting command, and I'm gonna actually select this face to be my inlet boundary. Well, actually, before doing that, I'm gonna hide some faces so that you would have a better understanding of why I'm actually selecting this surface. So I will have to select this surface and then use hide faces command. You can easily see that this is the front part of the truck, so that the reason that I selected this boundary to be my inlet boundary is that this is the location that the airflow will enter the computational domain. So I select this surface, right click on it, and then select create name selection option. I will name it as inlet boundary, and of course let me just rotate this geometry. Of course, this surface would be the outlet, so I will select it and name it as, let's just say, outlet. the bottom wall, of course, would be the location where we would name it as, let's just say, bottom. And what we're going to do next is that we're going to select all the surfaces related to the geometry of the truck. But that would be hard. Just to select all of the surfaces one by one. So we're going to actually use this trick. We're going to hide all of the faces in our domain using the hide faces, and after that you can easily see that what is left is only the surface or geometry of the truck. While actually having the face selecting command enabled, when you actually right click on the blank space in the graphics window and then select the select all option, all of the surfaces that are shown would become selected. And for this case, since we haven't hidden any face of the geometry related to the truck, all of the surface and faces of the truck would automatically become selected. So I will then right click on them and then use the create name selection option, and let's just name it as truck. Okay, now we're going to actually we can actually use this naming section in the ANSYS meshing itself. So in the ANSYS meshing commands later, and that is the reason why we recommend you that to define names for different surfaces of your geometry first before defining any mesh commands. So I'm gonna actually have to show all the hidden faces again in order to define the last boundaries. So the the two side boundaries along with the top boundary are the three left boundaries that we haven't assigned any name to. So I'm gonna actually select these two faces, rotate my geometry. I'm sorry, I'm gonna have to do it again. Select these two first faces, rotate the geometry, and then while holding down the control key on my keyboard, I'm gonna have to select the left surface. Name selection, and let's just name it as symmetry. And for the final part, we need to actually select the whole 3D object and name it as, for example, flow. Now this is something optional, and you can actually not do that if you are not willing to, because when you actually name this zone 3D object in the ANSYS fluent under the cells and conditions, you would be able to simply locate this 3D object and define any required material to it. This is actually useful when you have different zones and actually 3D objects in your geometry which you want to have different materials assigned to. So that's it for the name selection part. We have the inlet boundary, the outlet boundary would be the other side, bottom, and the truck itself, which is inside the geometry and we can't see it right now, the symmetry of all boundaries, and of course the 3D object, which is named as flow. After that, what we're going to have to do is that we're going to have to define some mesh commands for this geometry. So I'm going to have to right click on it, or right click on the mesh, go over insert, and then select sizing. As a matter of fact, you can actually select for the geometry. We're going to actually select the whole 3D object related to the domain, and then I will click on the apply button. In front of the type, we're not going to change the element size option, and as for the element size, which is the size of each mesh that is going to be placed inside this domain, I'm going to actually enter the value of 1 meter. But in order to create the smaller mesh cells that have better quality around the truck geometry itself, we can actually simply enable the capture curvature and proximity in order to as I mentioned earlier, create a smaller mesh cells around the truck geometry. So I will have to select yes for the curvature and select yes for the proximity. As a matter of fact, this curvature, as its name is obvious, create the smaller mesh cells around the curved parts. And as for the proximity, this option is used to create high quality mesh cells in the places where we have this narrow spaces between different objects. So that's it for the meshing command, and the next thing that you have to do is that you're gonna have to select and click on the mesh and then simply click on generate. After that, you're gonna have to wait for some more time until the ANSYS meshing software creates the the defined mesh type over your geometry. Alright, as you can see here, the ANSYS meshing software has generated the needed mesh over our geometry based on the specifications that we have defined under the body sizing command. And in order to actually show you the inner mesh, you can actually see that the mesh cells around the truck geometry are smaller in size when comparing to other mesh cells inside the domain. But however, in order to show you the inner mesh, we can actually use the section plane, and then as I select this command, I'm gonna have to draw a line passing exactly in the middle of my geometry, and then the software will automatically show you the inner mesh. In order to turn these mesh cells into a 3D format, I'm gonna have to select this option, show whole elements. Now as you can see here, the mesh cells are shown in better style. Alright, as you can see here, the mesh cells are like this, and you can easily see how they are smaller in terms of size when comparing to the mesh cells inside the other parts of your domain. Regarding the the number of mesh cells, you can easily see that if you actually expand the statistics, you can see the number of nodes and number of elements that are present in your model. For example, for this geometry, we have almost 3 million mesh cells generated. And regarding the quality or other parameters related to this geometry, you're gonna have to expand the quality section, and for the mesh metrics you can easily for example change it to element quality, and you're gonna have to wait for some time, and the software will give you a report regarding the quality of the mesh cells generated here. For example, you can see that the quality of the mesh cells that we have in our geometry right now is in a good range, and we can actually simply use this mesh in order to perform our simulation. So for the next step, you're gonna have to close the ANSYS meshing software and open the ANSYS Fluent in order to continue with your simulation. Alright, after creating a mesh for your geometry, as you saw earlier, I closed the ANSYS meshing software, and then in the workbench environment, you just have to double click on the setup in order for the Fluent launcher window to show up. Alright, in this section under the options, make sure that you enable the double precision, and regarding the number of processors, based on the number of cores you have on your own CPU and want to actually participate inside the simulation, you can enter a number. For example, I have 8 cores on my CPU, so I enter the value of 8, and then I will click on start. After that, you just have to wait for some time until the Fluent software opens up. The software is now building the mesh and actually reading the nodes and elements. As we actually had 3 million mesh cells in our geometry, it might take a little bit more time for the Fluent software to load it up, so we're gonna have to wait more. Alright, the software has read the mesh file, and we can start with the simulation settings in order to set them up. Alright, we will first start by the general task page, and I'm gonna actually start with the mesh section. If you click on the scale button, you can see the extents of your geometry and domain. For example, based on the outer domain that we have defined for the truck which is placed inside this domain, the minimum value for the x was -15, while the maximum value for x was 35. Same thing can be said about y and z. And of course, under the view length unit, you can see that the lengths that we have used in our geometry and model is in meters. Alright, for the next step, if you click on the check button, the software will automatically start checking your mesh for any errors, whether you have any, I don't know, invert mesh cells or mesh cells with negative volume. If you didn't have any problem with that, the software will show you this done report. And for the next step, if you click on report quality, the software will check the quality of the mesh cells that are generated inside your domain. Now, the most important qualities that the Fluent software reports for your mesh would be the orthogonal quality and of course the aspect ratio. As you can see here, the software is giving us a warning regarding that the minimum orthogonal quality of, I don't know, one or more than one mesh cell is in our domain is less than 0.01. So what we can actually either do is that we can actually either change the tetrahedral mesh cells that we have in our domain into polyhedral by using this make polyhedral command, or we can actually use the command, the TOI command that has been mentioned here. We're going to actually first use the make polyhedra in order to not only improve the quality of our mesh cells, but to change the type of these mesh cells from tetrahedral into polyhedral. So I'm gonna have to click on this make polyhedra, and you can easily see that the software gives you this information that it's converting the domain into polyhedra. So we're gonna have to wait for some time since the number of mesh cells in our domain was not very small, about 3 million mesh cells. The software is still trying to convert the tetrahedral mesh cells into polyhedral, and we're gonna have to wait a little bit more. Alright, it seems that the software has almost finished the setup, and we will be able to see the new mesh cells soon. The process is almost finished. The software is only optimizing the polyhedral mesh in order to increase their quality, and I think that would be the last step in this process. And after that, all we have to do is to simply click on display in order to show the new mesh cells. Alright, as you can see here, the software is making us aware that the process has been done, and we're going to actually have to click on display and display again so that the new mesh cells are shown. Alright, as you can see here, the tetrahedral mesh cells has been changed, and they are now turned and converted into polyhedral mesh cells. Now, in order for you to see the inner mesh, all I have to do is to simply disable these outer domain boundaries like bottom inlet outlet symmetry and only show the truck. Okay, now you can see the mesh cells on the truck. Still the mesh cells, the polyhedral mesh cells on the surface of the truck are much smaller than the polyhedral mesh in other regions of our domain. Alright, now if I actually click on report quality again, you can easily see that we don't have that warning, the minimum orthogonal quality, which was less than 0.01 in the tetrahedral mesh cells. We wouldn't have that warning anymore. Alright, regarding the display, as I showed you earlier, under the surfaces you can select all of the needed surfaces based on what you want to see, or actually disable them, and then by clicking on display you would be only able to see the selected regions, locations and geometry in your graphics window. Also, if you actually uncheck the edge command and then click on display, you would be able to see the geometry itself. Okay, now I'm gonna close this window, and for the next part, if I click on the units, you can see different parameters that may be used in our simulation or not. And if you actually click on each of these parameters, let's just click on length, you can see different units that are available inside the Fluent software for you to choose them. Alright, we're not going to actually change anything under the units, and for the next part we reach to the solver section. Under the type you can see that we have selected pressure based type of solver because the flow field that we're going to investigate would be incompressible because of the velocity of the fluid that we're going to define in our domain. And regarding the velocity formulation type, we have kept the absolute option because we don't have any parts that have rotational or translational motion inside our geometry and domain. And of course, regarding the time section, we have selected a steady time because we did not want our results to be a function of time. And of course, regarding the gravity, since the gravity doesn't play any important role in this kind of simulation, we actually don't need to enable it as well. So for the next part, we go to the model section, and because in this project we're only going to investigate the aerodynamics of this truck along with its container, I'm gonna actually double click on the viscous in order to define and select the model which I'm going to use in order to solve the turbulent fluid equations. Now for external flows, which are mostly used for aerodynamic analysis, it's better to use a k-omega model, preferably SSD k-omega model, in order to investigate the aerodynamics of, for example, airflow around any object of interest. But it should be mentioned that when using the k-omega SSD, of course, you're going to have to pay attention to the value of y plus. Now the value of y plus is something that shows you whether you are solving the flow field around and near to the wall boundaries correctly or not. And regarding the value of y plus, when using the SSD k-omega model, you have to make sure that that y plus value has the value between 0 and 1. In that way, you can be sure that your simulation process is correctly conducted. However, in case if you actually perform the simulation and saw that the value of y plus is much more than 1, then you're going to have to go back to the ANSYS meshing step in order to make your mesh cells smaller so that you would reach the y plus value less than 1. Alright, regarding the options section, you can easily see that you have different options such as curvature correction, corner focal correction, production limiter, and so on. Regarding the curvature correction, for example, as its name is obvious, it is mainly used where we have curvature, very strict curvature in our domain where we want to exactly model the flow behavior on them. And of course, another important thing would be the production limiter. Now, when you actually enable this production limiter, it prevents the generation of excessive turbulent kinetic energy over the stagnation points. For example, in this project, where we are actually pushing the airflow, for example, over the surface of the truck, we would have this stagnation point at the front of the truck, and very its pressure would actually increase due to that stagnation point. And this region is susceptible to increasing in for the turbulent kinetic energy, which might be not physical, something that isn't correct. So it's better for us to preferably enable this production limiter in order to prevent that case from happening. Alright, we're gonna have to keep this SSD k-omega model and move on to the next part. And as was mentioned earlier, we will perform the simulation and in case the y plus value was actually bigger than 1, we're going to have to go back to the ANSYS meshing in order to make our mesh cells smaller. So for now, I'm going to actually keep on moving and going further inside the settings that I'm going to apply for the Fluent software. For the next step, we're going to have to go to the materials section. If you actually expand the materials, you would see that you have two different materials of the names of fluid and solid. Of course, in our model, we only need to define the fluid material because the domain that we have defined in this project only contains fluid. So if I expand the fluid, you can see that the air material is automatically defined here. If I double click on the air material, in the shown window, you can see that under the properties section, of course, you can see the properties such as density, viscosity, which are defined for the air. Now you can actually change these properties manually and by yourself based on the simulation and based on the settings that you're trying to actually employ and perform on this simulation. You can either keep the air material by default, or if you wanted to add another material, you can simply go to the Fluent database section and select your desired fluid material from the list of available materials in the Fluent software. If the type of material that you wanted to add wasn't available here, you can simply define its properties, the needed properties that are shown here manually. So that's it for the materials. Next, we're going to have to go to the cell zone condition. If I expand this, you can see that since we only had one type of domain, which was the airflow domain, we only have this one cell zone. If I expand it, you can see that the flow cell zone is shown. If I double click on it, in the shown window, the most important thing that you have to pay attention to is the material name. Now for this simulation where we only have one cell zone and where we only have one material, the air material is selected automatically in front of the material name. But if you had actually defined let's say different materials than the air, then you would have been able to select that material here and actually change the material name from air to any other material that you have defined. And in that case, the material that would be flowing inside your domain would be that defined material. Alright, I'm gonna actually close these sections, and for the most important part, we've reached the boundary conditions. In this part, I'm just gonna change them to zone type. You can see different boundaries based on the names that we had defined in the ANSYS meshing software for different surfaces. So I'm going to start by selecting the inlet boundary. As I click on this inlet boundary, you can see that the type of this boundary is shown to be velocity inlet. When this type of boundary is selected for a surface, it means that you have to define a velocity magnitude for example, flow. In this case, the airflow. That is going to enter through this boundary. So if I click on it, click on the edit button underneath it, in the shown window you can see that under the momentum tab the software is asking you for the velocity magnitude. This velocity magnitude is the value of the velocity of the air that is going to enter through this inlet boundary. So actually I'm going to enter the value of 10 meters per second for the airflow. There's no need to change this supersonic initial gauge pressure value, and we're gonna have to actually keep it to 0 Pascal. And of course, regarding the specification method, we're going to keep the intensity and viscosity ratio. Alright, as I was saying, for the specification method, we need to select the intensity and viscosity ratio. Now regarding the turbulent intensity, it is defined as the ratio of velocity fluctuation to the mean flow velocity. And for internal flows, the turbulent intensity can be calculated through the shown correlation, in which the Reynolds DH is the Reynolds of a fully developed duct flow. For example, at Reynolds number equal to 50,000, the turbulent intensity is equal to 4% based on the shown correlation. Also, regarding the turbulent viscosity, it is directly proportional to the turbulent Reynolds number. Its value is large in the order of 100 to 1000 in high Reynolds number, boundary layer, shear layers, and fully developed duct flows. However, at the free stream boundaries, like what we have in our model right now, for most external flows, it is fairly small, and its value is in the range of 1 to 10. So as you can see here, the software has selected the value of 10 by default, and we're going to actually keep that value without any changing. So I'm going to actually click on apply button. And regarding the outlet boundary, if I click on it, you can see that its type is defined as pressure outlet. Let's just click on the edit button. And as you can see here in the appeared window under the momentum tab, the software is first asking you for a gauge pressure. Now this gauge pressure and the value that you define here would be applied over the outlet boundary. The gauge pressure value that we define here denotes the difference that exists between the pressure of the outlet boundary surface and the atmosphere pressure. So as you can see here, when we define this value to be equal to 0, we're telling the software that we want the outlet boundary to have the atmosphere pressure. So basically the airflow will enter through the inlet boundary to our computational domain and will exit it through the atmosphere. The same thing can be mentioned for the turbulence, as we actually mentioned it earlier in the inlet boundary. Regarding the symmetry boundary, there's no need to actually do any specific settings. And next we're going to actually click on each of the wall boundaries. Both of these wall boundaries would have same settings, so I'm just going to show you one of them. Alright, after clicking on the edit button for the bottom wall, for example, you would see that stationary wall motion along with no slip shear condition are defined here. Regarding the stationary wall, you may think that the truck is moving through the air. So basically, the truck should have, translational velocity. But in that case, you should probably think about the relative velocity theorem. We can actually say that the truck is moving through the air, or we can actually push the air to pass over the surface of the truck. Both of the cases would have same meaning. So in this case, and in this project, we have actually pushed the airflow velocity from the inlet boundary to pass over the surface of the truck with the velocity of 10 meters per second, and we have actually kept the truck geometry stationary. So that's it for the stationary wall case. And regarding the no slip, we all know that with the airflow velocity or any material's velocity would reach the value of 0 specifically near to the, for example, a wall boundary. So when we actually enable this no slip boundary condition or shear condition, we're telling the software that for example, in this case, the airflow velocity will reach the value of 0 when it is very near to the surface of for example, a solid, which in this case would be our truck. So that's the reason behind selecting the no slip shear condition. Alright, as was mentioned earlier, the truck wall boundary would have the same settings as the bottom wall boundary, so I'm going to actually close the boundary conditions and move up to the next part, which is the methods. Now in the methods section, the most important thing that you need to select would be the pressure velocity coupling, or in other words, the algorithm you want to use to solve equations related to pressure, velocity, etc. Now if I click on this drop down list, you can see that there are 4 different algorithms defined here. The first 3, meaning the simple, simple C, and piezo, are iterative algorithms. However, for the coupled, as its name is obvious, the equations related to pressure, momentum, etc. would be actually solved together and in tandem. Now, the upside of using coupled algorithms comparing with the other algorithms available here is that when you actually use the coupled algorithm, you would get a more robust simulation and more accurate results. However, it should be mentioned that when you're using this coupled algorithm, you need to have more computational resources comparing with the 3 other iterative algorithms, because in these 3 algorithms, meaning the piezo, simple C, and simple, the equations related to pressure, momentum, etc., anything that you have in your model would be solved separately, and actually it's some sort of algorithm in which you will first solve, for example, the velocity formulation, and then you will solve, for example, the pressure, and then using an correcting equations, you will correct the values related to the each of the components of velocity and pressure. So in terms of computational resources, these three algorithms, meaning the iterative algorithms, are much more thrifty comparing to a coupled algorithm. However, it should be mentioned that the obtained results may have reduced accuracy when compared to coupled. So in this project, which is not a very complicated project, I'm going to actually use the simple algorithm in order to continue. So I will select the simple, and after that we need to define the discretization method that are used for each of the parameters that are going to be solved inside our simulation. So for example, for the pressure, you can see that by default the software has selected second order upwind. For the momentum, second order upwind, turbulent kinetic energy, second order, and also the specific dissipation rate, second order upwind, has been selected as well. Now regarding the other options available here, you can see that if I click on each of these drop down lists, you would be able to select, for example, among first order upwind, quick, third order MUSL, and actually for this type of specific type of simulation, we can simply change the turbulent kinetic energy and a specific dissipation rate discretization method to first order upwind, because we don't actually need very high accuracy simulation results, and in order by simply changing them to first order upwind, we can reduce the computational time and resources that we need. Also, there is no need to enable this warp phase gradient correction. This is mainly used where we have high quality mesh cells and that we want to increase the we want to actually decrease the solution time. But in this project, this is a very simple project where we don't actually need to enable any of these settings underneath here. Next, we will move on to the controls part, where we need to define the under relaxation factors. Now, as you can see here, these under relaxation factors here are defined automatically by the software based on the models and the software and the simulation you're trying to perform. These actually under relaxation factors have values between 0 and 1, and based on the type of simulation and project that you're doing, you can change these URFs in order to obtain, for example, a better convergence rate, or actually prevent the fluctuations in, for example, a parameter. But it should be mentioned that if you plan to make changes to these under relaxation factors, you need to have a in-depth understanding and experience of how to change the under relaxation factors in order to get a correct along with converged result. So it is highly recommended that you do not change these values, because most of the times changing these values without any prior experience would result in divergence. And also for this specific simulation that we're doing, since this is a very simple project, there's no need to change these values and we can move on. Alright, the next part would be the report definitions. Now if I right click on it and go over new, you can see that there are different types of report you can define here. For example, surface report, volume report, force report, flux report, etc. Now regarding the simulation or projects that we mainly have in aerodynamic field, we would like to calculate, for example, forces like drag force, lift force, or even their coefficients. So in this specific project, in order to calculate such forces, we can simply go over force report and then select, for example, drag, lift, moment, or any other type of force which would be explained. Now let's just say that we would like to calculate the drag force due to the airflow passing over the surface of this truck. So I'm gonna actually click on drag, and in this section you can actually define the name of this report. Let's just say I'm gonna name it as drag. After that, under the report output type section, you can select between the two options of drag coefficient and drag force. Now regarding the drag coefficient, as you all probably know, it has its specific and its own formula in which you have to define, for example, a correct value for the section area of the truck. But since we don't have that exact value, we're gonna actually have to select the drag force so that the software would calculate the drag force for us, and shows it to us when it's performing the simulation. But more on the drag coefficient. If you ever actually decided to perform a simulation in which you wanted to calculate the drag coefficient, you just have to make sure that you define correct values under the reference value section. For example, as I double click on this reference values, you can see that the software is asking you for reference values such as area, density, enthalpy, etc. For the cases where you want to calculate non-dimensionalized numbers, such as for example this drag coefficient here, or lift coefficient, or Reynolds number, or Nusselt number, or any other type of non-dimensionalized number, you have to make sure that the values that you define here for the reference values are correct. And when you actually correct these values under here, you would be able to calculate the drag coefficient or non-dimensionalized numbers correctly. However, if you do not change these values, or actually change them into correct values, you wouldn't get a correct report out of this report definition. Alright, so as I was saying, I'm gonna actually select this drag force here, and as for the zones, I'm gonna select the truck because this is the surface that I want to calculate the drag force, the exerted drag force on. So I have selected the truck, and for the next important part, I'm gonna actually discuss force vectors. As you can see the direction of the truck, you would easily understand that the airflow is in the X direction. So when you want to correctly calculate the drag force, you have to tell the software what is the direction of the airflow. In this case, for example, by incident, actually the value that we have defined, that value that has been defined here, is 1 for the X direction, while the Y and Z direction have the value of 0, indicating that the airflow is in the X direction and parallel to the X coordinate system. So that's it. But let's just say that we wanted to calculate the lift force. Then in that case, since the lift force is perpendicular to the flow direction, then we would have had to define the value of Z equal to 1, let's just say, and turn the value of X equal to 0. In that case, we would have calculated the lift force. But since we have selected the drag force here, I'm going to change it back to what it was. And that's it for the force vectors. It should have been mentioned. And also regarding the create section, if you enable the report file option, the software will generate an external file of the changes in the values of the, for example, drag force as you progress through the simulation. And of course, if you enable the report plot, the software will show you the changes in the drag force over the surface of the truck inside the graphics window. So it's up to you. It's totally up to you. You can actually enable both of them, or you can actually disable, for example, the report file if you don't want an external report file. Also, if you enable the print to console, you would be able to see the values of the drag force and its changes for each iteration as the simulation progresses. For example, let's just say I don't want to generate an external file, so I'm just going to disable this, and then I will click on OK. Now, regarding the report definitions and the value that you will see, for example, for the drag force in this project as we go through the simulation, it is some sort of auxiliary monitor mean, so that you can actually understand whether your simulation has converged or not. Of course, the first mean of convergence would be the residuals, and if the residuals reach and get nearer to the 0, you can say that your simulation has reached convergence. But the values, for example, under the report definitions should be checked. For example, for this specific case, we can say that our simulation has converged when the value of the drag force reaches a constant, for example, value. In this way, actually by checking the values of the drag force and checking the residuals, you could be saying that your simulation has converged or not. Also, regarding the residuals, which was mentioned earlier, if you expand the monitors and then double click on the residuals, in the appeared window you would be able to see the names of different parameters that are going to be solved in your model. For example, in this project we're going to solve continuity, x velocity to z velocity, k and omega parameters. In front of each of these parameters you would be able to see a value by default 0.001 under the name of absolute criteria have been defined. Now, these values indicate that whether the residuals related to each of these parameters reaches a value less than this value, then the software would count that parameter converged. So, in order to make your convergence rate stricter, or get a more accurate result, you can simply reduce this value, as you saw I did, so that the software would iterate more on that parameter in order to obtain this, in order to reach this absolute criteria. But regarding this changed value, I'm going to change it back so that we would use the default values. Okay. For the next part, I'm gonna click on initialization button, and in the middle part of the software window you can see that we can select between the two options of hybrid and standard. Now, regarding the hybrid initialization, in this method the software will automatically calculate the needed values for actually the initial values needed for each of the parameters to be solved by actually calculating and using a Laplace equation. However, in the standard initialization method, you get to define those initial values which are needed for solving the PDEs related to each of these parameters and equations manually. It should be mentioned that based on the values that you define here, your simulation may converge sooner, but that doesn't make that much difference. So a better way for you is to a way to have a better initial guess is to select, for example, a boundary from different boundaries in your model. Let's just say I'm going to select the inlet boundaries, and then the initial values related to each of these parameters would be taken from the inlet boundaries. So I'm going to select this one, and you can easily see that the x velocity value changed to 10, while the values of z velocity, turbulent kinetic energy, and a specific dissipation rate changed as well. So that's it for the initialization part. I'm going to click on the initialize. For the next part, which is the final step, we need to double click on the run calculations button and define a number of iterations for our simulation process so that it would start calculating the mentioned parameters and equations. Let's just say I'm gonna enter the value of 1000 and see what will happen to the residuals related to each of the parameters and how the drag force changes as we go through the simulation. So as I click on the calculate button, you would be able to see that the software will start the simulation process, and you would be seeing that the software would start showing you the changes in the residuals for different parameters shown here. This is the scaled residuals, and of course this is the drag report that we have defined. After this, you're gonna need to wait for some time until the software performs the simulation and give us the results. Alright, as you can see here, after almost 100 iterations, the simulation process has ended, and you can easily see the behavior of the residuals reaching to a reasonable value. So this is for the residuals. These are reasonable. We can say that based on the behavior of residuals, our simulation has converged. However, I should check the changes of the drag as well. Now, as you can see here, when the simulation is started, we had a very large value for the drag. However, as the simulation iterations passed on, you can easily see that the value for the drag has reached a constant state and constant value, showing us that the simulation process is probably converged. So that's it for the residuals and the drag, and now we need to actually export results in order to see whether our guess regarding the convergence of our simulation was right or not. So I'm going to start by extracting some graphical data. In order to do that, you can actually go over graphics and expand it, and then double click on the contours button. In this window, first make sure that you disable the global range, because if this one is enabled, any of the contour or data that you extract would be shown with the legends, based on the values, based on the global values. You may actually, for example, let's just say you want to calculate the pressure over the surface of the truck itself. The legends shown on the left side of the contour would be based on the total values of the pressure in your domain. So you don't want that to happen. So you may want to actually disable the global range. So when we were talking about the pressure. So let's just start by extracting the pressure distribution over the surface of the truck. Under the contours of section, you have to select pressure, and then of course under the surfaces section, you can simply select the truck. As I click on the saver display, you can easily see the pressure distribution over the truck surface. So I'm going to zoom in. As you can see here, the pressure has its maximum value on the front area of the truck, which is the place where the air reaches the stagnation point, and has the velocity of 0. And as we actually move along the truck, you can easily see that the pressure reduces and decreases. This is actually the changes in the pressure. You can easily see that. Alright, for the most important part, we need to calculate and extract the, for example, velocity contour. For extracting that contour, we need to define a plane or isosurface passing from the middle part of the, for example, truck. So in order to do that, I'm going to have to right click on surfaces, go over new, and then select isosurfaces. Now the plane that I'm going to create is parallel to the ZX plane. So we can simply select mesh here under the surface of constant, and underneath it we actually need to select the y coordinate, because we are going to define the value of y for this surface. So I will have to select y coordinate, and if I can click on compute, you can see that you can see the extent of the geometry or domain in the y direction, which is between -15 meter to 15 meters. So if we wanted to place this surface in the middle of our geometry, we need to make sure that this ISO values has the value of 0. So as I click on the create, surface is created underneath it. I will go back to the contour number 1, and I'm going to change it to, for example, velocity, and under the surfaces I'm going to select y coordinate. Now as you can see here, let me just make it okay in terms of visualization. Alright, now as you can see here, this is the velocity distribution of the airflow passing over the truck geometry. As you can see here, behind the truck we have this wake region where the velocity value has decreased, and you can easily, for example, let's just say you can easily see the airflow boundary layer starting to separate from the surface of the truck based on the shape of this frontal area. And these are actually the places where we would have the highest drag force generated due to the pressure difference that exists between different surfaces. The most important part, which has the effect on the value of the, for example, drag force, is this area where you can see the wake region. You can actually I'm gonna actually show it to you, where you can see the path lines and actually streamlines and in this area you would be able to see them having this vortex effect. Alright, that's almost everything that we could have extracted from the velocity contour. So let's just move on to something else. I'm gonna actually come back to the turbulence and show something to you after I showed you the path lines here. So I'm gonna actually how about extracting velocity vectors? That would be a better mean for showing these vortexes. So as I double clicked on the vectors, and in this window all you need to do is to first change this style to field arrow, and I'm gonna actually discuss this scale later. And under the surfaces section, make sure that you select Y coordinate and then click on save display button. So as you can see here, these are the velocity vectors of the airflow passing over the surface of the truck and over the generated surface, which was the Y coordinate system. Alright, I wanted to show you the vortices that are generated behind the truck. So in terms of a scale, you actually you can easily see that the arrows behind the truck are very small. You have two options. You can either increase the scale. For example, let's just increase it to 5 and see what happens. This scale actually has effect on all of the velocity vectors in your domain, and you can easily see that when I increase the scale, the length of the velocity vectors behind the truck increased, along with the length of other velocity vectors in other areas. So I'm going to actually increase it again. For example, let's just say 10 and see what will happen. And now you can easily see those velocity vectors that I was talking about. You can easily see the vortices generated behind the truck, showing you the wake region that has been created due to the shape of the truck and the fact that airflow velocity is passing over the surface of the truck without being able to attach to the solid surface, which causes these flow separations. Regarding the other option that you had in order to better visualize these velocity vectors, is that you can click on vector options and then click on fixed length, and we can actually together see what will happen. And then I will click on apply button, close, and then I click on save. Now you can easily see that the velocity vectors, all of them actually right now have the same length. Which may not be very physical, but in terms of just visualizing and seeing what is happening in there, it's a good option. So I'm going to disable it again, apply, and click on save display button. Now you can easily see that the velocity vectors have turned back to their right scale. Alright, that's it for the graphics part. You either can actually extract some path lines as well. Let me just show it to you. So actually, after double clicking on the path line, you first want to decrease the steps and the number of steps you want to have in your model, because having a lot of steps in your in this window and actually making the software to calculate each of these surfaces as one strict line or streamline would demand high computational resources. So I'm just gonna reduce this value and then increase this value step by step so that the software is able to calculate the streamlines without any effort. Also, regarding the path skip, which is the number of paths we want to skip in these 100 steps, let's just enter the value of 5 and see what will happen. Also, under the color by section, let's just select velocity, and this means that we want these path lines or streamlines to be shown based on the velocity of the airflow. So reader can select the inlet boundary so that the path lines of the airflow entering through the inlet boundary are shown, or we can actually simply select the truck so that we can see the path lines, the airflow path lines exactly passing over the surface of the truck. So I'm going to select this truck, and then I will click on save or display button. The software is still trying to show you the path lines. You can see that we have decreased the steps from 500 to 100, and the software is still trying to calculate them, let alone keeping that to 500 steps. Alright, it seems that we're gonna need to have wait for some time. Alright, it seems that it is, yeah. You can easily see the path lines originating from the surface of the truck, and in terms of the, for example, path lines behind this, I don't know whether you can see this or not. You can easily see though the path lines, becoming involved inside the mentioned vortices, and you can easily see how they are behaving behind the truck. However, the other path lines passing over the surface of the truck may hamper this visualization, but still it is evident, and you can easily see how the wake region causes the airflow path lines to behave. That's a very good result, and you can actually use this to understand the behavior of the flow behind such objects. Now, as was mentioned earlier, this wake region creates a very large amount of drag force over the truck surface and geometry. Alright, that's it for the graphical part. We're going to actually close the graphics, and for the next part I'm going to show you how to calculate the final value of the drag force or lift force or any type of force in your model. So I'm going to actually expand the reports, go over forces, and you can easily see that you have three options of forces, moments, center of pressure. Regarding the force, as was mentioned earlier, if we want to calculate the value of drag force under the direction vector, we need to enter the value of x equal to 1. Now, also under the vol zones, you can see that the truck has been selected by default. So if I click on print, under the console tab, you can see that the software will show you the values for the drag force. Here you can see that you have two parts. The first part shows you the values for the force, while the second part shows you the value of the coefficients. Now, as was mentioned earlier, since we didn't correct the reference values in this part, actually, we cannot say that the coefficients that are calculated here are correct. So we're going to ignore them, and we're going to actually only focus on the forces section. Alright, you can see that the software is giving you a report regarding the drag force that is applied over the truck surface, and this drag force is divided into two different parts: the pressure part and the viscous part. As you all know, the drag force is composed of two main parts, which is the pressure and the viscous tensions. So as you can see here, since we have this wake region generated behind the truck, the majority of the value of the drag force is due to the pressure differences that exist in your model, and a very minor value, a very small value, is because of the viscous tensions that are applied over the surface of the truck. So that's it. You can see the pressure induced drag force, which is equal to almost 500 newtons, and the viscous induced drag force, which is almost equal to 30, and the total would have the rough approximate value of 531. Also, let's just say, for example, you want to calculate the lift force as well. So I'm going to have to change this value to 0 while setting the value of 1, y equal to 1. So as I click on the print, the force that you are seeing here is the lift force. So you can see that the same can be said about the lift force. It composes up from two different things: the pressure induced lift force and viscous induced, and the total has been shown here. Again, the coefficients are not correct. And that's it for the force part. You can actually extract moments. Now, this moment is mainly used where you have, for example, rotating parts in your geometry, and this is actually a thing that you can use to calculate the torque that is applied to a specific region, for example. In order to do that, you can simply have to define the center point of the location where you want to calculate the torque that is applied on. and you have to enter that its location and coordinates here. And then regarding the moment axis, you want to actually define the direction of the axis, of that location which the torque is applied on. So since we don't have any rotating parts in our geometry, this moment option is not something that we can use. So that's it. That's what you could have actually extracted from this project. But before actually finishing the tutorial, I'm gonna have to show you something else. As you all can probably remember, we talked about y plus value when we were talking about the SSDK omega model that we have used in this project. As you remember, I mentioned that when we are using this SSDK omega model, we need to make sure that the y plus value over the surface of the truck is actually less than 1, is between 0 and 1. So in order to calculate the y plus value, I'm gonna go to the turbulence section, and I'm gonna select this vol y plus, and under the surfaces I'm gonna select, let's just say, truck, and click on save or display button. This is the vol y plus contour over the surface of the truck. Now if you pay attention to the values for vol y plus under the minimum and maximum section, you can easily see that the maximum value of the y plus over the surface of the truck is way more than 1, which indicates that the mesh cells that we have used over the surface of the truck is larger than what it should have been. So in order to correct the value of the y plus when we are using the k epsilon model, we need to close the Fluent software and then open the ANSYS meshing software again. I'm going to actually show it to you. Okay, for this part it's just showing you a warning indicating that whether you want to save the present data and settings or not. Let's just change it to use settings changes for current and future calculations in order to not have any problem in the future. I will click on OK, and the software will exit and the Fluent software will be closed. I'm just gonna have to wait for some time until the data is saved. Alright, I'm gonna have to go back to the ANSYS meshing. And again, we're gonna need to wait for some time. Alright, we mentioned that the reason that we actually get high values of y plus is that the mesh cells that are placed over the surface of the, for example, truck are very large. So in order to make that smaller, we can actually perform this face sizing command. And regarding the geometry here, we need to select all the surfaces of the truck, but as you all can probably remember, we had previously done that by giving names name to different surfaces of the truck. So in front of the scoping method, all you have to do is to change it to name selection, and as for the name, you can simply then select truck. In this way, all the surfaces related to the truck would become selected without any effort. Alright, for the type, we're gonna keep the element size, and for the element size, let's just say I'm gonna enter the value of, as you all can probably remember, the body sizing was set to 1 meter for each of the mesh cells. So I'm gonna actually enter the value of 1/10 of that value. So I'm gonna enter the value of 0.1. Again, let's just say capture curvature and capture proximity are enabled, and do the meshing again. This time we're gonna have to wait more than the first time because the software will create a smaller micelles over the surface, so it may take much more time. Alright, as you can see here, the mesh generation process is finished, and comparing to what we've seen before, the mesh cells placed on the surface of the truck is much smaller than the previous mesh cells now. So you can easily see them right now. In order to actually compare it explicitly, you can easily see that the number of mesh cells has increased. You can actually perform the simulation, the exact steps that we did exact steps we did earlier on this mesh, and see whether the values of the y plus decreased to value between 0 and 1. If yes, then that is a sign that your simulation is completely correct, and you can actually say that your results are correct without any flaws. So I'm gonna actually leave it up to you as an exercise, so that you can perform the steps of simulation again and see whether the current mesh is good enough for the simulation using the SDK Omega model or not. If not, you're gonna have to come back again and make the mesh cells on the surface of the truck smaller again, and then perform the simulation again until you get the correct value of the y plus. Good luck. To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com, or please visit our website www.mrcfd.com.